Okay, so and now I'm going to tell kind of a very different thing, which is much simpler than what we studied before, and it is called a method of characteristics. And it is for first order PDEs. So, and I'll go in the direction of increasing complexity. So, let us start from the very simple equation. So, equation is this one: dt of u plus sum of vi d over dxi v vi of x. Maybe we can write it as a v gradient. Maybe we can write like du over dxi equals to 0. So it is the simplest possible equation. By the way, have you already learned about the vector fields? So we know that first order differential operator is identified with the vector field. What is written here is the vector field acting on a function u. So in principle, differential geometry teaches us that when we have such a situation, then what does it mean? That if we consider from I equals to 1 to n, we can say that there is this r n plus 1, and there is this vector field dt plus sum of vi d over dxi. So one point of view is that there is this vector field in the space of vector fields on this Rn plus 1, we can draw it somehow. So this vector field goes like this, and this equation tells us that our function is constant is constant along this vector field. So u is along this vector field. So it should be possible to solve this problem explicitly, and also to find these lines on which this v should be a constant. We need to solve equation of the flow of this vector field, and this equation is the following one. So let's consider the following system of ODEs. So it's a system defining the flow of this vector field, and it is like this: dx over dt equals to v of x, with the initial condition x so with initial condition x0, in a sense that we have some x which depends on t and x0 initial x. So x of 0 and x0 equals to x0. So we can solve this system and find something like this. There is, of course, a question about solvability, and we can encounter many problems, but all these problems are actually the problems of this first-order differential equation itself, because its solutions can behave quite badly. But suppose that we know this solution and such function of x that satisfies this equation. And now let's consider and suppose that u solves this ODE. So maybe let us denote it by star and denote this by 2 stars. And we can also add initial condition to this. So when we have first derivative, then it is of course natural to say that u of 0 and x equals to some u0. So let us add it here. So u of 0x equals to u0 of x. So it is our equation if you want to solve. So u solves this equation, x solves this. And consider u where we substitute a solution of this equation instead of x. U of t, x of t, x0. So now try to differentiate this. So d over dt, u of t, x of t, x0 will equal to du over dt. Derivative in the first variable plus du of this arguments t, x of t, x0 plus sum from I equals 1 to n dx of dx of t x0 over dt du over dx xi over dxi. case. So we see that this combines precisely to this operator. We can actually introduce the notation that dt plus sum of vi d over dxi denoted by a big dt. This notation. So we see that here it tells us that this time derivative of this expression equals to this this is called probably material derivative or convection derivative, which corresponds to change in time and the change of point on this vector field. So this derivative in time equals to this dt of u. And a statement that this derivative is zero is precisely this equation. So it is zero. This u is really constant along this integral lines of this vector field. So if you, so it means that we have some surface of where we define initial conditions and say that there is this vector field and there are its integral lines. This first order equation can be restricted to a single line. So if you go along this line, then this equation turns from PD to ODE, and it describes in this case trivial evolution of U. So if it was some U0 here, then it stays U0 with this evolution. So solution of this equation is therefore U of t x of t x0 equals to U0 of x0. And if you want to find an expression of u like a function of t and x, you should solve this equation. You should recover x0 from known x of t. So you should find a point which came to this particular x in time t. Or, in other words, you can run this evolution of the vector field in the opposite direction. So this is the general solution. So is it clear, obvious, and so on? So this was for this simple case. But now we see that we can, in principle, make this equation more complex. Namely, we can. In this case, we see that equation is that u should be preserved along this integral line. But if it is preserved, then no one can prohibit us to add this u as a function of this vector field. It will just mean that for different values of u, we will have different vector fields. So So the first grade of complexity is this one. So maybe I can number these equations. So the first, so it is kind of first simplest equation. Then on the first upgrade is that we can add here, let's second level. We can add here dtu plus the sum of vi of u and x du over dxi equals to 0. So in this case, what happens? We can see again that this equation can be written as well, it is just equivalent way to write it to say that dt of u equals to 0. But now this vector field depends on u. So a characteristic of this equation should be this one. Dx over dt equals to v of u and x. And now again, if you consider such a derivative, so dt of u, and now now gives what? Again, 0. So now maybe let me say it better. Okay, here we should actually say that it is a self-consistent assumption to say that u as a function of t is a constant, because it equals to 0 from one side. So this u is constant, and we can say that it is this derivative dt of u, which is 0. So here again, this u is constant on the integral lines, which now depend on u itself. And let us consider an example of such equation. So 1D hydrodynamics. Dt of u plus u u dx of u equals to 0. So in this case, which equation, what equation we need to solve? This equation is x dot dx over dt equals equals u, right? So x equals x0 plus ut, and so we know that if we substitute this to our u, it should be constant on this characteristic. So u of x 0 plus u of t x0 plus ut equals u0 of x0. So what is written here? It is some equation on function u of x and t. So let us write it somehow. So one way to solve this is to say that so let me think. So so we want this to be a function of u and x. We want to find u at a moment t. So let us write it as u of t and x equals u0 of x minus u of x and t. So it is some equation on function u of x and t which should be solved. We can so there are two questions. First is to verify that it is actually a solution. So let us first do this. So we have this equation, and let us try to differentiate u of t and x. So dt u of t and x equals to, we can just write u0 prime, and here it is minus ut of t and x. That's all. And the dx u of t and x equals to u0 prime times 1 minus ux of t and x. So hmm? Yes, thank you. Yeah, I missed one term then. Thanks. Minus dut minus u of t and x. And here we have t ux. So we have this. So there are still equations on this derivatives of u. But let us expand them from this equation. So we see that ut of t and x equals to minus u over minus u times u0 prime over 1 plus t u0 prime times, like this. And ux of t and x equals to just u0 prime over 1 plus t u0 prime. So we have this, and when we add them, we see that u ut plus ux equals to 0 actually. So this equation actually defines us some function u which solves this one-dimensional hydrodynamics. And now let us. Are there any questions about this? So let us draw some pictures. So suppose, maybe, let me divide this into 4 parts. So suppose that we have initial profile u0, which is of this kind. This is u0, this is x. And we can mark here the parts with a constant u. So we can imagine that there is some distribution of particles which move with velocity u, and we have particles that move with such velocity from this point to this point, and so on. So it's such a mixture of them. So it's kind of explanation why this is a solution and how to think about this. So when t equals to 0, it just says that u of 0 and x is just u0 of x. But what happens when we turn on some time t? Now, if you want to find u at some if we want to find u at some point, for example, if we want to find u for this x, we should take a value of u0 at the coordinate x minus corresponding u. So so suppose that it is ut. So the value at this point will equal to the value at this point before. And if you go down, then the smaller this velocity is, then the smaller corresponding shift is. So kind of upper part of this hill move faster than the lower part. So so in the next step we will have a picture like this. So it will be, so this part becomes much steeper than this one. So this part's past a longer distance. This is u of t and x. This is x. And at some moment, we see that particles with higher velocities can move further than particles with a smaller velocity. And the picture in this case will look like this. So. So this font it's called probably overturn, something like this. So this equation at some moment this equation starts having non-unique solution, and we see that there are some points where, for example, x derivative of u is infinite now. So, and it is a very typical situation for this first order differential equations. So for higher, or if you had higher derivatives, then this phenomenon can be smoothed. So is it fine? No. And we can. Hmm? Hmm? No, it's not a function, it's multivalued. Yes. we can consider some simple example probably. No, no. Okay. So can we consider something simple? Mm. Maybe and simplest and but very stupid example of this problem in the following one. Let us say that initial u is minus alpha times initial u of x is minus alpha times x. So if we substitute into this equation, then u of t and x will equal to minus alpha x plus let me think. Yes, it's fine. Alpha t times u of t and x. And if we now find this u, so it develops singularity in finite time. So it is such line which rotates, and at some moment it becomes vertical. Actually, it's funny that this solution is also a solution of a KdV equation. So if we add here third derivative of u, or even the second derivative, it will still be a solution because its x derivative is x derivative, second x derivative is already zero. So such a funny solution. And also, if you look at this equation, we can write it like this. So let us say that u0 has an inverse function. So it is of course not true in such case when it's not so when it has several values twice, but it can be true locally. So we can introduce the inverse function like u0 of phi of u equals u. So kind of u0 combination with phi equals to identity. So inverse function. So and using this inverse function, we can rewrite this equation like u0 like phi of u maybe no, I should have taken inverse in the opposite direction. So no, phi of u0 of x equals to x. So phi u0. So this function tells us what is x at which this function u equals to this particular value. So if we apply it to our solution, then we have that phi of u of t and x equals to x minus t u of well, let me at this moment erase the arguments of u, because I want to show some trick. Phi of u equals to x minus ut or tu. So this is an equation which relates three variables. So, and we know that if we write u as a function of what was that, t and x, then ut plus ux equals to 0. So it's one case. Another case is that we can consider not this dependence, but we consider x as a function of t and u. And it is very easy to write an equation which is satisfied by this x. It is just here. Maybe let me specify it explicitly. This partial derivative is a partial derivative with fixed x, and this partial derivative is du over dx with fixed t equals to 0. So when we have this, then we should so we can write the following: dx over d no wait. Need to think about this well. Maybe in this case it's wrong idea. No, probably no. No, it's fine. Dx over dt with fixed u equals, or maybe I can write it like this, minus u equals to 0. That's all. Because when we differentiate in t with fixed u, derivative of this left hand side is 0. And this procedure, I mean, inversion of the function, like from u of t and x to x of t and u, is called a method of Godograph. So, mm, and physically, it means to transition from this collective description of particles which have some distribution in velocities to keeping track of some particular bunch of particles which move with velocity u. And I think so it can be applied to other nonlinear equations, but all the cases which are so can be understood without this formal computation, like how to differentiate functions with different variables fixed. It usually can be understood in such a physical ways that we look at a particular particle and see what happens with them. For example, we can solve in this way a equation for one-dimensional gravitating particles. So in that case, gravitational force is a constant, so it depends only on the number of particles to the left of this particular one. So it is clear that such problem can be exactly solved. Yeah. So are there any questions about this? So now let us move to the next upgrade of this equation. So it is a kind of a third level of complexity. So for now, we had everything time independent, but of course we can try to add some non-trivial function here. So namely, let us write an equation of this kind, of dt of u equals to some function of u, t, and x. So in this case, we need to solve an equation. So basically, this says that our function should evolve with time, and we solve an equation of this form, like dx over dt equals to v of t, or maybe of u, t, and x, and du over dt equals to also to this f of u, t, and x. So by x, I mean this x which depends on time. So if we now if we now consider our u as a function as a function of this point, So now consider u as a function of t and x of t. And act to this with this derivative, then oh my god. So we again see that it equals to dt of u, and it equals to this f of u, t, and x. Well, this equation can also be solved in this way. I don't know. Is it clear, or it should be said a little bit more rigorous? We basically say that we take so we want to find this u on this characteristic line of this system of equations, which also depend on u. So we start at some point, and mm, and we keep track of u, t, and x. So, so all these three functions evolve somehow, but we know that at each time this function u is assigned to a point to point x of t. So this is so here we have u of u of t and x of t, and the value which should be assigned to this point is given by a solution of this equation. So we construct solution on this line, and when we try to differentiate it, when we act with this differential operator, this coincides with with a time derivative on this characteristic. So if you solve this equation and assign u by this rule that that u of x and t is a solution of this equation, then derivative of this of function along each characteristic is correct. It is f, and uh, we can glue the whole solution from such characteristics. So we need to consider all possible initial points and reconstruct u of t and x of t on each of these lines. So, and this will be the solution of this equation, which you see now it is still first order in derivatives in derivatives of u, but now it can be a nonlinear in u itself, and this nonlinearity can be everywhere. So, and so can I go further? So now maybe it's the last upgrade, because we already have an equation which is nonlinear in u but linear in derivatives. So the last step is to consider equation which is nonlinear also in derivatives. And well, globally, it's of course not always true, but locally we can solve this equation for the for derivative in one specified variable. So let us say that we have some preferred variable t, and write this expression, this equation like d s over dt. Well, actually, maybe it's first upgrade. Actually, now I would like to simplify it a little bit in the sense that I want this equation to be s independent. So I want an equation which depends only on s and its derivatives. So its equation is goes to zero. So it is called a Hamilton-Jacobi equation. By the way, have you seen it before or not yet? Hmm? So you already had it, right? Yeah. So, and probably some particular solution of it, which was needed for separation of variables, right? So now I want to tell a little bit difference in like so for a long time I was wondering like how to solve how to find the general solution of this equation, not that particular one which is needed uh, for classical mechanics. And it's funny that it's actually easier to understand the answer to this question from quantum mechanics, from quasi-classical limit, than from classical mechanics itself. But if you try to upgrade this approach, then it is also clear. So. So how to solve such equation? Let us try to introduce the new functions like API equals to ds, and this is like in this code action. Let us introduce APIs which equal to ds over the dxis. There are such functions. And the question is how they evolve with time. So let us compute d pi's on dt. This equals to minus so it equals to d2s over dt dxi. And so if we exchange the derivatives, it equals to, better to say, so it is d over dxi of this minus d over dxi of this Hamiltonian, which depends on PIs of x and axis. So when we differentiate it, we will have two parts. One comes from explicit derivatives in x, so it equals to minus dh over dxi. And another comes from differentiation of these p's themselves. Minus sums of dpi over dxj dh over dpi. So we realize that this can be combined to the following expression, like d over dt pi d over dt plus sum of dh over dpi so d over dxi acting on API equals to minus dh over dxi. So we see some candidate for this we see a candidate for the vector field, which can be responsible for our Hamilton-Jacobi equation. So let us say that dt equals to d over dt plus sum of dh over dpi d over dxi. And now we see that like dt acting on p equals minus dh over dxi. Dt acting on x equals to maybe it's not very useful, because we know that this is the vector field, and if we want to compute the whole the vector field, we should integrate equation like x dot equals to dh over dp. But it's also nice that it can be written in terms of this material derivative. So it equals dh over dpi. And the last question, so who is ds over, so who is dts? So and the answer is this one. dts equals to, first we should write this derivative. So it is sum of dh over dpi pi minus h. And so if you look at this system of equations, we see that there are some that there are some functions p and s, and all of them are differentiated along the vector field defined by these equations. So pi, so dpi over dt equals to minus dh over dxi. Dxi over dt equals to dh over dpi. So these are Hamilton-Jacobi. These are Hamilton equations from classical mechanics. And the last equation tells that S equals to S0 plus the integral from 0 to t. So this expression is called Lagrangian of the mechanical system, from 0 L dt. So so the answer is that if you want to solve this Hamilton-Jacobi equation, then so we need to solve these equations with initial conditions given by x's and derivatives of this function, like s of x of t x 0 ds over dx 0 ds 0 over dx 0 s of t comma this one equals to s0 of x 0 plus integral from 0 to t. This Lagrangian computed on x of so it's actually a function of x and its derivative. So So the picture again is the same. So we have some surface of initial data. We have some S0 here, 0 of x, and we have some. I cannot draw it, but we can imagine this function as some kind of density, and we need to find characteristics which are defined not only by the initial point but also by gradient of this function. So, and depending on gradient of this function, we have some characteristic, and the value of s on this line is given by the action of a mechanical system described by this Hamiltonian. So is it fine? So here we have s of x of s of t x of t of x 0 and yes or dx 0 somewhere here. Oh, in principle, it seems to be more or less clear that we can make this Hamiltonian also a function of s. We can add it here explicitly, and it will mean that this last equation, so all these equations will be kind of coupled system of equations for s, x, and p. So we can do this fifth upgrade to make it nonlinear also in s, but I'm not sure that such equations appear in the applications. So I know in this example of Hamilton-Jacobi equation, but concerning this equation linear in S, probably it can appear somewhere, and it can also be solved by the same method. So the summary of all this is that any equation, so any linear equation which contains only first derivatives of function s can be reduced to some system of ODEs. And as a consequence of this is that its solutions can have a huge number of singularities because these characteristics can intersect. And it turned out that, for example, also like in this case, this function can become non-single valued because several characteristics can meet at a single point, and each of them is saying that the value of function is this one, another is saying that the value of function of that one, and it leads to such multi-valued functions. It's very typical. So maybe I can add here the remark that just to fix it, that ds over dt plus h of s ds over dx x equals to 0 is also solvable. So, uh, so are there any questions about this, about these equations? So, mm. But by the way, in principle, we can try to consider an example of this Hamilton-Jacobi equation for the free particle. Uh, so let me maybe erase something. Uh, Let me write this. So it is d s over dt plus 1 over 2m ds over dx squared goes to 0. But it's actually not very interesting because so we can write it as t plus 1 over 2m s x squared equals to 0. But I don't want to solve it actually because let us look at the hydrodynamics equation. So it looks like ut plus ux equals to 0, which can be written as ut plus 1/2 u squared x equals to 0. So if you now say that u is well, let us put m equals to 1 for simplicity. So let us say that u is sx. Let us define it this way. Then this equation says that s tx plus 1/2 s x squared x equals to 0. So probably up to some constant, we have that sx plus plus st plus 1/2 of sx squared equals to a constant. So and we can reabsorb this into s. So if we define s tilde equals to s minus ct, and then s tilde t plus 1/2 s tilde x equals to 0. So if we know how to solve hydrodynamics, then we can we also know how to solve this Hamilton-Jacobi for the free particle. And let us actually look at that particular solution for the free particle. So we had this solution which was maybe let us for simplicity take limit alpha to infinity. So there is the solution u equals to x over t. And if you now say that u is sx, then s equals to x squared over 2t. And if you now So it is clear that it is a solution of this equation, and the interpretation of this solution is quite simple. That it is a reaction for the particle. So it is integral from 0 to t for x dot over 2 squared. It's an action on trajectory which let me maybe write it like this: t minus t0, x minus x0. It is also a solution, but in this case it will be more clear what is the meaning: x0 squared or t minus t0. So we have a particle. We have a free particle such that x of t0 equals to x0, and x of t equals to x. So it means the parameterization of this trajectory is x0 plus t x minus x0 over t minus t0. Let me use big letter for this purpose. So x of t, it's the trajectory of this particle which passes through this point. And if you compute an action on this trajectory, s on x is integral from t0 to t 1/2 of x dot squared dt. So dt. So explicit computation tells us that it is precisely this x minus x0 squared over 2 t minus t0. Like this. So let me tell also another story, which is now about second order equations. So let's consider the following equation. Like or probably plus some first derivatives. Oh, we can add them. In principle, we can have something else. And I want to say that the main the leading part of this equation can be reduced can be and let us also consider for simplicity matrices maybe it could be uh, um, matrices with a negative determinant. So this is equation, and this is a wave type equation. It also works for elliptic equations, but better to think about the hyperbolic one. So the determinant is less than 0. So statement is that this can be put to canonical form. There exist such coordinates xion of x and y and eta of x and y. So this A depends on x and y, and B also depends on x and y, and C depends on x and y. Such that this equation is d2u over d psi d eta plus something else equals to 0. So, and why is it true? So, if we have such a metric with a negative determinant, it means that it is of type 1 minus 1, so it is of type dx squared minus dy squared. So, or it can be written as so if we define quadratic form, g of so if we define quadratic form of this kind, a dx squared plus 2b dx dy plus c dy squared, maybe. If we define such quadratic form, then it has 0 directions. So there exist such vectors that exist some such vectors like v1 and v2 such that g of vi equals to 0. Like if we have a quadratic form dx squared minus dy squared, maybe better to rewrite it as dx minus dy times dx plus dy. So it is kind of dx plus and dx minus. So if you substitute vector dx plus on both positions, dx plus, it will be 0. And g of dx minus is also 0. And and those are only such vectors. So it is clear that this scalar product gives a product of two components, product of plus and minus components, and the two possibilities when it is 0 is that either we have a vector with only the first component, or a vector only with second component. So quadratic forms with a negative determinant have two preferred directions. So we can think about this like so. If we draw lines like if it is Vx and it is Vy, so lines when g of v is constant are such hyperbolas. And there are these preferred directions for which this quadratic form just vanishes. And if we upgrade this local analysis to the whole R2, then what we see? So there is this R2, and there is some family of lines. I don't know how what is the best picture, but in principle there are some lines of this kind passing through each point, such that vectors tangent to these lines. Okay, if it is a tangent vector like v plus or v minus. So these vectors correspond to these zero directions of our quadratic form. So g of v plus equal to 0, and g of v minus also equals to 0. So if we now choose if we now try to choose parameterizing these lines as two coordinates. So let us choose coordinates in such a way that this line corresponds to like xi is constant, and this line corresponds to eta equals to constant. So if we do this, then we will have necessarily that then that our quadratic form of dxi will be equal to a quadratic form of d eta, and will equal to 0. So and if it is true, then our metric becomes some function of psi and eta, of psi and eta, dxi d eta, and so we are done. This leading part of Laplace operator reduces just to this mixed derivative. And how to find such lines? Well, it is written here. So they're described by condition that a matrix should vanish on such lines. So we just need to write this equation: 0 equals to a xy dx squared plus 2b of xy dx dy plus c of xy dy squared. So it can be considered as an equation for a dx over dy. So it means that dx over dy equals to what? Minus b over a plus minus a square root of b over a squared minus c over a. And so this gives us a equation for it gives us some equation which can either be solved or cannot be solved analytically. But if it can be solved, then we have some x equals to function of y and some initial condition like c. But better to write it as there is some function f of x and y equals to c. So this is a description of a solution of this equation. So and this c should be chosen as a new coordinate. So here it is, for example, c plus, if we choose here plus, and we also have the same equation. What is f plus, and we also have another equation, dy equals to minus b over a minus square root of b over a squared minus c over a. And so in this case, if we have some other function of minus of x and y equals to c minus, and this c's can be chosen as a new coordinates. So now du over dc plus dc minus plus something will be 0. Oh, in principle, what can we have here? We can have some first derivatives plus some p plus du over dc plus p minus du over dc minus plus some u equals to 0. So and depending, sometimes we can be lucky in the sense that, for example, if this expression was not some random combination, but if it was the actual D'Alembert operator written in this curved metric. Then what we get will be just a second derivative, because it will be the D'Alembert operator in the metric given by some function times dxc d eta. And there is a nice property in 2 dimensions that this D'Alembert is given by the following expression. It is square root of g d over no, g I j d over dx dxi 1 over square root of g d over dxj. And if we choose a metric of this form, so if g ij is equal to 0, some function phi 0, when we have only off-diagonal components, then oh, so value, then a determinant of j equals to so absolute value of the determinant of j equals to phi squared, and so square root of g times gij, which is inverse metric, equals to just 0, 1, 1, 0. And it means that this D'Alembert, in this case, equals to just phi d2 over d, wait, and this plus this minus. So the point is that even if we work in some curved metric, but it is in 2 dimensions, then wave equation has absolutely the same properties as in the flat metric, because we have this kind of how to say it. So all metrics in 2 dimensions are conformally equivalent to the flat one, in the sense that they can be given by some function times flat metric. And so if you solve an equation D'Alembert of something equals to 0, then D'Alembert of u equals to 0, then u is again some function of c plus some function of c minus. So, but if we try to add, for example, some time derivative, then this conformal factor becomes essential. And the same is also true for elliptic equation. So if we choose here a positive determinant of a matrix, then it will be in some sense a little bit more complicated, because these characteristics should be complex, and new coordinates should also be complex. But we can think about this as about analytic continuation. So so if you want to solve a Laplace equation in 2D, then it does not matter which metric is given to us, because because a proper choice of coordinates becomes it conformally flat, and in conformally flat metric, Laplace, the number operator, is some function, conformal factor, times usual second derivative. For Laplace equation, it would be d2 over dz bar. So, and these lines are, as far as I know, they are also called characteristics, because they are also solutions of some first order equations, and they are kind of auxiliary for some PDE. But their nature in this case is a little bit different. So, are there any questions about this? Oh, maybe the last short story. It's about equations which look nonlinear, but in reality they are linear. So let us consider the heat equation. And this is u t equals to u xx plus, let us put here some number nu. Oh no, let us put some number nu here. So there is this equation. Of course, we know how to solve this. But let us now try to consider the following function. Let us consider how to call it. Let us consider s, which equals to ux over u. So then sx will equal to uxx over u. Let us actually put number nu here. Minus nu ux over ux over u squared. So we can say, and so we can compute this function, and we can also compute function s at t. This one equals to new utx over u plus new ut ux over u. Mm, Moment. Hmm? Hmm? Yes, yes. Thank you. Yes, thanks. Sorry, I didn't do this computation for a long time, so yeah, yeah, I forgot to bit what precisely should be done. So mm, so basically we want to write equation on s on this function. So to do this, we just substitute. So st equals to so this a new tx over u can be written as new squared u xx over u minus new uh, uh, u squared again uh, uxx over u squared, and uh, then uh, we notice that it is mm, so we want to write it as a derivative of uh, is is new squared dx of uxx over u, right? Mm. Here it seems that this works, and now we substitute this using this formula. So we can write that uxx over u equals to 1 over nu sx plus 1 over nu squared s squared. It isn't this one. So let us substitute it here. It is nu s squared dx. Maybe we should have put 1/2 somewhere, but it doesn't matter. Dx of 1 over nu sx plus s squared plus 1 over nu squared s squared. Yeah, finally this one. So st now becomes nu sxx plus 2s sx. So, and if you don't want this if you don't want this 2, then we should say that 2s is some s tilde. In this case, this s tilde t will equal to nu s tilde xx plus s tilde sx tilde. So you see that this equation so is it fine or not? I don't know. Sorry. Maybe I've chosen the wrong letter for this S. Maybe it is better because it's not the Hamilton-Jacobi S. It is this one for hydrodynamics equation. So probably I should have used letter V for this, but I don't want to change its notations. So so it is no. So I'm stupid. Actually, I should have used let me maybe replace this with this one. So S will be replaced by V everywhere. So mm, and if you want to have a Hamilton-Jacobi equation, then we should say that S equals to a new logarithm of u. In other words, u equals to e to 1 over nu s. So in this case, if you substitute this, and then we will have an equation like d t s will equal to nu sx sxx plus sx squared. So in this case, it is Hamilton-Jacobi equation. And the meaning of this substitution is a kind of a transition from quantum mechanics when we have when nu is I times Planck constant, and this u is a wave function, and this is the classical limit of the wave function, and it satisfies Hamilton-Jacobi equation with quantum correction. And this is kind of relation between this hydrodynamics in 1D and Hamilton-Jacobi. So if you use this substitution, then we see hydrodynamics with this correction, and we know that heat equation does not have any problems with solutions. We can just write this representation. We can just write this integral representation for a solution, and in principle, it is possible to recover a solution of the of this equation. The limit nu goes to 0 by saddle point method, and it is written in the lectures. And by the way, this is called Berger's equation. And this is called probably Hopf transformation, and I don't know precisely how to spell this. So another option to modify this one-dimensional hydrodynamics is to add we can add here we can add here third derivative of x, and well, and this equation is not so trivially solvable, so we cannot write explicit solution, but it is a famous KdV equation, and in some sense it is integrable in the sense that it is possible to write everywhere dense a set of explicit solutions given by theta functions of some higher Riemann surfaces, like this V is given by some coefficient times d2 or dx squared a logarithm of theta on higher genus, some t v plus u plus x u plus w, and this one is integral. Okay, so maybe try out of time. Okay, so are there any questions about anything? Okay, so Thanks everyone for your attention. Thanks for attending the course. And have a good holidays and see you in the new year. Probably. Thanks.